Okay, hello everyone. I'm super bummed that I'm not giving this presentation to you in Athens. I would much rather be there than in my apartment, but I am here located in San Francisco, California, in my beachside apartment, so can't complain about that. And I'm really excited to be talking to you all today about research that I've been conducting since I joined Cobalt.io, which is a pen testing as a service company out here in the Bay Area. Um, so a little bit about me, replicant tendencies, but probably organic. I started my career in Washington, D.C., where I was mostly focused on nation state actors and doing a lot of work in the national security and cybersecurity policy arena concerning APTs. And then last year, I moved to San Francisco to work for Cobalt, which is a pen testing startup in San Francisco. And a lot of the work that I have been doing has been around the value of vulnerabilities. So that spans from bug bounty to pen testing to sort of what dynamic scanners bring to the table, and helping us sort of assess what that means for application security. So my co-researcher on this is one of our technical program managers, Travis McCormack. He is a badass data wrangler, used to work at Walmart doing pen testing for Walmart, and has the OSCP. So a little bit about this talk, human or machine, the Voight Kampff test for web application vulnerabilities. Some of you may not know this. I don't know how many of you in Greece have actually seen Blade Runner. It's I think it's like a 1980s movie in which police officers are hunting down robots who masquerade or appear like humans, and the Voight Kampff test is a test conducted by a corporation to figure out if someone is a human or a machine. So my question for you, the question that this research presents is, why does method matter? Why does it matter what vulnerabilities are discovered by humans or machines? Because in the end, a vuln is a vuln. No matter the method through which a vulnerability is discovered and reported, for the purpose of security, the goal is the same. If you're responsible for protecting software, you want to find and remediate as many vulnerabilities as possible to reduce the likelihood of a breach. Or if you are a black hat hacker, you actually want to increase the efficiency of identifying vulnerabilities to increase the likelihood of a breach. We're actually seeing this in cybercrime. We're seeing a lot of trends around automating crime, right? I mean, even things as simple as like malware as a service is now propagating. So we're seeing efficiency, we're seeing competing efficiencies on both sides, right, between black hat and white hat hackers. There is also a very legitimate business case for discerning between human and machine. Analysts actually predict the global application security market is going to grow up to $9.64 billion by the end of 2023. That's a compound annual growth rate of 24.95%. An industry that's nearly $10 billion. Imagine telling that to a phone freak in the 1960s who would face basically criminal charges for essentially identifying business logic flaws with telephone companies. The market is rising to the demand, and today there are hundreds of companies geared towards application security. Scanners that cost tens or even hundreds of thousands of dollars are competing against open source tools. We'll talk a little bit about that later. And the efficacy of some of these tools remain unclear. Freelancers are looking for the same bugs that a specialized pen tester working for a consultancy is searching for. Results-oriented work is now pitted against time box work. The question of human or machine is now a question of ascertaining value in a results-driven market. It's now part of the strategy for choosing vendors, allocating resources, and determining the best use for InfoSec's greatest scarcity, which is time. Okay, so let's dive in a little bit. I chose web application vulnerabilities for a reason. From the data I can find, web apps continue to be the most tested for pen testing, at least. As you can see here, more than 65 of our pen tests that Cobalt conducted last year were web apps or web apps and APIs. And what about bug bounty? Bug bounty is the same. HackerOne says bug bounty hunters predominantly hack web apps. For bug crowd, 90% of the targets were also web apps. I would love to see some research on other targets like external networks or cloud configuration. I think it's a great area for a future research project for someone. But for the purpose of this talk, I'm sticking to what's most valuable. Okay, so a little bit about this research. The scope of this research is dynamic scanning pitted against black box testing. This includes out-of-band scanning, which finds vulns like second-order SQL or blind cross-site scripting. I'll go into that in a little bit more detail later. We wanted to answer 3 questions. What vulnerabilities can dynamic scanners find? What are the vulnerabilities that only humans can find, like dynamic scanners cannot reliably identify them? And then what are the vulnerabilities for which scanners will not automatically populate results, but where automated tools can enhance efficiency to conduct further exploitations? We generated input from Cobalt CORE, which is our pool of roughly 300 freelance vetted pen testers. They had a lot of opinions and a lot of disagreements, which is great. And then for the examples I pulled for this presentation, I relied on public bug bounty reports, OWASP examples, and PortSwigger. I would have loved to have pulled from Cobalt's results, but we actually don't disclose customer vulnerabilities, even if they're anonymized. And of course, humans can have a little proxy as a treat. I'll get more into that later. Okay, so what kind of web application vulnerabilities has Cobalt been finding? First off, we're finding a lot of vulns. Misconfiguration continues to dominate. It's a pretty broad category that ranges from cookie attributes to business logic bypass. OWASP lists misconfig as number 6 in its top 10 web app security risks. But for the second year in a row, misconfiguration leads in our findings, followed by cross-site scripting attacks. It's a little bit hard to see the data here, so I'm just going to read it off for you. It's misconfiguration, cross-site scripting, authentication in sessions, other, sensitive data exposure, missing access controls, insecure object reference, components with known vulnerabilities, cross-site request forgery, redirects and forwards, server-side request forgery, and remote code execution. Okay, so here's where the machine wins. It's pretty comprehensive if you see this. Dynamic scanners work, as many of you know, by injecting malicious payloads. They test access points when they are communicating with the front end. Scanners are programmed to understand arguments and function calls, and they can detect vulnerabilities in headers, verbs, fragments, and DOM. They can also identify some misconfigurations and find components with known vulnerabilities. One of the disagreements among our pen testers was whether scanners could reliably find trickier vulns like second-order SQL or blind cross-site scripting. As many of you know, a standard cross-site scripting or SQL attack, for instance, produces immediate results, like an alert prompt that says, "Hello world," or data spilled into an input field. When you see that, you can immediately recognize the success of a payload. But what happens when a payload is successfully injected, but the vulnerabilities output isn't produced immediately? Blind vulnerabilities mean the request or response is obfuscated in some way, making it difficult or impossible to interpret. And then out-of-band vulnerabilities means the response does not return within the same interface through which the attack was sent. With blind or out-of-band vulnerabilities, you actually won't see the vulnerabilities output immediately. This is often because an application activates the payload at a later point, thus requiring the pen tester to have back-end knowledge of the system to know if the payload was successful. If there's no echo in the cave, are you yelling loud enough, or is it actually a tunnel? I've concluded that for the purpose of this research, the answer is yes. Machines are awarded blind, second order, or otherwise out-of-band vulnerabilities. You might be asking, okay, why the asterisks? It's there for a reason. Scanners still require manual setup and produce a significant number of false positives. So a human will have to configure any scanner and sift through results. Also, as many of you know from running your own enterprise scanners, like they produce a ton of results, and you actually have to go through them and figure out what's positive, what's a false positive, what's a true positive, and then also be able to figure out what's a priority for you, right? So even if a machine can actually report certain vulnerabilities, it's still going to require a human to go through and actually figure out what the hell's going on. And then here's just like a couple of examples of some open source scanners out there. There could be an entire talk on the efficacy of certain scanners over others. Some companies claim their tools can find a certain vulnerability. Some other companies might dispute those claims with their competitors. I'm not going to say some of these companies are lying, but let's just say the results can prove inconsistent. Yeah, like maybe a scanner could find a certain type of vulnerability, but with a slim success rate or a high false positive rate. You know, with a ton of configuration, maybe a scanner could find a certain type of vuln. You know, it depends. So I highly recommend checking out Shay Chan's research comparing the price and features of web app scanners on the market, both commercial and open source, and you can ping me at any time and I will provide that for you. Okay, so here's where things get fun. We debated this among the Cobalt core, and as I said earlier, there was not complete consensus. But the 3 vulnerability types that we generally agreed upon that only humans could find were business logic bypass, race conditions, and chained exploits. So I'm going to provide you with some cool examples just to show you exactly what happens with these kind of vulnerabilities. And we'll, you know, to give you a better understanding of why humans excel at finding these. Okay, so the first is business logic bypass. I just pulled this from a bug bounty report. It's a really great example. A few years ago, a handful of core pen testers worked on a bug bounty for Uber. What they found was a pretty interesting business logic bypass that led to an IDOR. So how did they do it? First, they figured out that any user could create a driver account, but that account couldn't be activated until Uber verified their driver documents. You couldn't access the Uber driver app until you were verified, or at least that's what Uber intended. When looking at the request screenshotted on the left, you can see that there's a parameter called allow not activated that was set to false. So what happens if you set it to true? Well, they actually obtained a valid session token. No bueno. In the response, there was a field called is activated set to false. When you change that to true, they were able to access the driver app. This later allowed them to access another driver's name, license plate, last trip UUID, last passenger name, number of passengers, origins, and trip destination through an IDOR. As my colleague Travis likes to say, building stuff is hard. It's way easier to break things than it is to build things. Business logic attacks exploit design flaws or unanticipated abuse of business logic, like having a user controllable parameter that is trusted. Business logic bypass requires thinking about an overall system architecture. It's contextual. One of the things that I've really learned in the last year through doing this research and my own experience doing web app pen testing is how important the fundamentals are. A lot of this is actually is about understanding the principles behind how a web application is functioning, understanding the architecture, understanding exactly what programmers were deciding when they built this application. So it really requires taking both a 3,000-foot view of the application and also diving in and seeing exactly what's wrong. So the other one that we agreed on was race conditions. First of all, I love the handle cash money. It's like an amazing name. Second of all, I could paraphrase this vuln for you, but Shopify actually explained it really well in their bug bounty report, so I'm just going to copy exactly what they said. Cash Money reported it was possible to bypass the email verification process in a partner's dashboard. Doing so would have allowed a partner to request access to a store under an email address the partner did not own. If a store had a staff account associated with that email address, the staff account would have been automatically converted to a collaborator account and added to the partner's dashboard without any merchant interaction. We tracked down the bug to a race condition in the logic for changing and verifying email addresses. We fixed it by locking the database record during these actions and requiring store administrators to approve all collaborator requests. So in my opinion, this is also another clear example of understanding business logic as well. To really excel at finding vulns like this, you have to understand the intended processes driving the business and ask yourself, but what if I tried this instead? For cash money, the answer to this question was $15,250 for a time of check, time of use race condition. Honestly, in my opinion, pretty well deserved. As I said, the Shopify bug was exploited through a time of check, time of use race condition. As you see here, there's a multiple step process to successfully exploiting this kind of vulnerability. Race conditions are caused by not locking a file, meaning there is a race between when a file is open and not locked by the process. It was bad with Shopify, but you can probably imagine how even more serious a race condition is for a bank, like when approving a transfer. I am sure that some of you are sitting on your hands right now, believing that scanners can find race conditions. Some of you probably think that the machine deserves to win this one. Can a scanner find this? Actually, yes, a scanner can, but it has to be source code review or static analysis that would probably be able to find this. Race conditions are probably found through a fuzzing tool as well, but that's not the same thing as a scanner. And fuzzing isn't necessarily a function of a vulnerability scanner. It doesn't actually tell you what the vulnerability is. You have to find what breaks first through fuzzing. So basically, I tricked you all a little bit. Scanners can theoretically find race conditions, but not dynamic scanners, not without like a huge amount of configuration or like a very specialized tool. And it would probably need to be some sort of static analysis that finds that, or you would need to use fuzzing to find a race condition. And in that case, I don't qualify fuzzing as a scanner because it doesn't identify the vulnerability. Okay, last up is chained exploits. I think this is self-explanatory, so I'm not going to get too in-depth here. The example I included is actually one from one of our core pen testers. I'm just going to read off the HackerOne summary for you. Shopify infrastructure is isolated into subsets of infrastructure. This bug bounty hunter reported it was possible to gain root access to any container in one particular subset by exploiting a server-side request forgery bug in the screenshotting functionality of Shopify Exchange. Within an hour of receiving the report, we disabled the vulnerable service, began auditing applications in all subsets, and remediating across all our infrastructure. The vulnerable subset did not include Shopify Core. After auditing all services, we fixed the bug by deploying a metadata concealment proxy to disable access to metadata information. We also disabled access to internal IPs on all infrastructure subsets. We awarded this $25,000 as a Shopify Core RCE, since some applications in the subset do not have access to some Shopify Core data and systems, do have access to some Shopify Core data and systems. So if you can find a scanner that can successfully find an RCE through server-side request forgery, I'm all ears. In the meantime, I think we can safely say only a human can find this. And I also just want to say, for the record, that chained exploits really prove that even if you find a low-level vulnerability, some simple cross-site scripting, for example, those can be used, right, to get to a more severe vulnerability. And so even if it's something that's relatively minor, it's always better to remediate it. I mean, a classic example, I reported for a bug bounty company recently when I was doing some hunting for them, something really simple as user enumeration, that I found. It's a really low-level thing. Like, it was just, that they didn't report the right error message. But even those minor things can lead to a successful brute force attempt, right? Which is one of the fastest and most common ways to hack into a web application. So I seriously recommend, you take every report you find seriously, and you do take a serious look at even the smaller or lower risk vulnerabilities that have been presented to you, because you just never know what could end up being chained. So the truth is, the Voight Kampff test is just not right. In pen testing, humans and machines rely on each other. Automated tools and scanners are intended to drive efficiency and enable human creativity, but working together, humans and tools are powerful. A classic example of this is, authorization flaws like IDOR, DOM-based cross-site scripting, RCE, session management, file upload bugs. Another one recently that I've been looking into is, which I'm sure many of you know of, is subdomain takeover, right? I mean, you can automate the shit out of that pretty easily and be able to find subdomains. You know, you don't need to go through and click on every single web page that you find. Scripts are available for you to do that, and then it's just up to you to figure out exactly how to execute. So just a case study for you to see this is IDOR. I just pulled this from Burp Suite or PortSwigger, you know, as an example of how to find this. You set up Burp Proxy, you send requests to intruder, you pick the position, you find a section of your URL that refers to an object, head over to a payload, tailor the number, and start the attack. And then you use the results to take other actions like enumerating accounts, right? So you go through and you see 200, 200, 200, great. Gives you a sense of what's going on. You know, then you can move from there. So basically the tactical takeaway for this, like what's the tactical takeaway? Tool price does not equal the quality of the results. So, you know, even if you are basically something like OWASP Zap, for instance, is a tremendous and powerful tool that you can use. It's free. It's a dynamic scanner that also does, you know, crawling for you as well to help you find and do recon on web apps. You know, there are a lot of really great open source tools out there that do a highly effective job at finding vulnerabilities. So I would not necessarily conflate price with quality. And the number of vulnerabilities that's reported does not necessarily mean the quality of the results too. As I said earlier, with chained exploits, you know, you do need to be aware of lower level vulns that are reported, because something as simple as like a minor, you know, reflective process scripting can potentially do more serious damage if it's chained. And then of course, creativity. If creativity is greater than narrow thinking, then you're going to find better vulnerabilities. You're going to, you know, maybe get more money if you're a bug bounty hunter, and you're going to have more fun. And when you're looking to hire a pen tester, you know, it's the same thing. You want someone who's able to think outside the box, and be able to think strategically and creatively, and also has a really good sense of, you know, business logic and the fundamentals. And so if you can take anything away from this talk, it's that humans and machines work together in finding vulnerabilities, and we have more fun that way. So thank you so much for joining me today. Like I said, I'm sorry that I couldn't be in Athens with all of you wonderful people, but hopefully we will unite another time. So yeah, thank you all so much.